In this video, I want to take a look at a coal-fired power station. I'm going to run you through all the systems, such as the electrical system, the condensate system, the steam system, the fuel system, the exhaust gas cleaning system, and the cooling system. We'll take a look at all of the major components of a coal-fired power station, such as the boiler, steam turbine, electrical transformer, cooling tower, electrostatic precipitator, etc. At the end of this video, we're going to take a look briefly at biomass power plants and waste-to-energy power plants. We're going to compare a coal-fired power station to these other types of power plants and look for the similarities between them. So here is an example of a coal-fired power station, also known as a coal-fired power plant. Over here we've got some coal storage areas. This particular design uses a covered coal storage yard. Quite often you'll see a coal storage yard that is open. That means there's no domed cover like is shown here. Within this domed shape would be coal, and the coal is going to be extracted via conveyors and delivered to our power plant, which is over here. Notice that the coal is delivered via an inclined conveyor, and that's because we want to carry the coal up to a high elevation in order that we can then drop it down into hoppers or storage silos. Within the power station, there's going to be day silos, and they'll store enough coal in order that the power plant can remain in operation for 4 or 8 hours or 12 hours, even if the coal supply system from the conveyors or even the coal yard should fail. So that gives us a bit of reserve within the power plant itself. Now, in order to discuss some of the other systems that we're looking at here, I'm going to use a different 3D model so that we can have a look at it all in a lot more detail. Here's our more detailed model. It's more detailed because, as you can see, there are a lot more internal components here that are visible. And as you can also see, if we come over here, it's quite complicated. So let's break this down a little bit and start with the fuel system. What we're looking at now is a water tube boiler, or at least the internal parts of it. We're going to feed coal into our boiler using these silos. There's 1, 2, 3, 4. And with this type of boiler, we feed coal into the boiler pneumatically via a coal pulverizer. The coal pulverizer is actually at the bottom here. It's this item, cylindrical in shape. There's also 4 of those, and they act independently of one another. We pulverize the coal and then feed it pneumatically into the boiler. The coal will actually come out through these holes that you can see in the side of the boiler, and they're on both sides of the boiler. The 2 main types of fuel feed system that you're likely to see are the pulverized type, which is the one we're looking at now, or the stoker type, which uses a moving grate in order to feed coal into the boiler. Those are the 2 main types that you're likely to see, so keep a lookout for a moving grate that feeds coal into the boiler, or, as you can see here, holes in the side of the boiler where we feed in pulverized coal. There's also a different type of boiler called a fluidized bed boiler, but this boiler design and its associated feed system is nowhere near as common as the other 2 types. So we fed coal into the boiler and we're going to get combustion. When we get combustion, the exhaust gases are going to rise up here, flow through the boiler, across all of these tubes, down here, along here, and then we're going to go into our flue gas cleaning system, also known as our exhaust gas cleaning system. I've now built that system. The first item that we come into contact with is an electrostatic precipitator. They look a bit like Lego blocks and they're all stacked together. Here we've got 4 electrostatic precipitators all installed together. The job of an electrostatic precipitator is to remove particulates from the exhaust gas stream. We don't want bits of dust and bits of carbon being expelled into the atmosphere, because if that happens, those particulates are going to gradually come down, land on fields, on people's houses and things like that. So it's the electrostatic precipitator, or the ESP, that prevents this happening. It separates the particulates out from the exhaust gas stream, typically with an efficiency in excess of 99%. We've then got a fan. This is an induced draft fan. We're going to induce or draw the exhaust gases from the boiler. The reason we have the fan here and not on the other side of the ESP is because if we have the fan, let's say here, All of those particulates are going to damage our fan blades as we draw the exhaust gas out of the boiler. If we put the fan on the other side over here, or the fans I should say, since there are two in this particular example, then the particulates would have already been removed from the exhaust gas stream, and that means they will no longer damage our fan blades. This also means that we have to do less maintenance on the fans, and it will require less parts. The exhaust gases then flow to this item here. This is our flue gas desulfurizer, or FGD for short. ESP, electrostatic precipitator, FGD, flue gas desulfurizer. The purpose of this item here is to reduce, almost to eliminate, the sulfur dioxide gas that's within the exhaust gas stream. We don't want sulfur dioxide because it can cause acid rain if it's in high enough concentrations, and due to ever more stringent environmental legislation, that is no longer acceptable. So we're going to remove as much of the sulfur dioxide as possible from our exhaust gas stream, and it's the FGD, the flue gas desulfurizer, that allows us to do that. The exhaust gases then pass into a cooling tower, but they're not cooled. What's actually going to happen here, if we go in through the top of the tower, you can see that the exhaust gases are ejected through this pipe here and the other pipe here. The exhaust gases at this stage are quite clean, and because of the shape of our natural cooling tower, air is drawn in at the base and moves in an upwards direction. It does this naturally, not only due to the shape but also because there's a lot of evaporation occurring within the cooling tower. We're using the cooling tower for what's known as evaporative cooling. So when this occurs, the air will be drawn in at the base of the tower, it'll be accelerated up and out the top of the tower, and as that occurs, our exhaust gases, which are going to be quite warm, they're also going to rise up and out the top of the tower because the density of the exhaust gases is less than the ambient air. If we have a cold gas, it's going to be more dense than a hot gas, and that's the reason these exhaust gases, with their lower density, rise up and out of the tower. As they do so, we're drawing more cold air in through the base of the tower, so it's quite an efficient process. And it's the reason we don't just send the exhaust gases out through a separate stack, instead of doing what we have here, where we send them into the cooling tower. But why are we burning coal in the first place? Well, in order to understand that, we've got to go back to our boiler, and you can see all of the tubes here. The tubes themselves contain water, and that makes this a water tube boiler. Let's add our water and steam systems. You can see now I've added the steam turbine and I've added also the water and steam systems. Water is going to be fed into the boiler via our deaerator. This is a deaerator. It's usually mounted quite high up within the power plant, and we do this because we want to have a positive head of pressure from the deaerator going downwards towards our boiler feed water pump. The purpose of the deaerator is to remove oxygen and other dissolved gases from our boiler feed water. If we go down from the deaerator, you can see that we've got a pump. This type of pump is a multi-stage centrifugal pump, and we're going to use it to increase the pressure of our boiler feed water. The pressure you're going to increase it to really does depend upon the boiler design. I'm going to say here about 200 bar, which is about 2800 psi, but keep in mind every boiler design is slightly different. We increase the pressure and then we're going to send our boiler feed water into our high pressure feed water heaters. We've got one here where my mouse is and another one here. So the first stage would be where my mouse is now, and the second stage is where my mouse is now. From the high pressure feed water heaters, we're then going to come along here. I'm not going to trace it all out, but I can tell you now the water is going to enter the boiler through this connection here. It's going to be heated up by this bank of tubes, and we refer to this bank of tubes as the economizer. From there we're going to take the water and send it to our steam drum, which is over here. Now I don't want to follow every single pipe through the boiler. It's simply enough to say that the water is going to be passed around through the boiler until it turns into steam. The steam is going to come out through this connection where my mouse is now. We're going to deliver that steam at high pressure to our steam turbine, which is down here. we have a high pressure steam turbine which is installed towards the left side of the screen, between these two lines. We then have an intermediate pressure turbine which is installed at the center of the screen where we're looking now. So those are the HP, high pressure, and IP, intermediate pressure, turbines. In this particular design, from the high pressure turbine, we feed the steam back into the boiler through this connection here, where my mouse is. It's going to be reheated. We'll pass it through a reheat superheater as well. And then we will draw the steam out through this connection where my mouse is, and we'll send the steam to our intermediate pressure turbine. So we've gone from the boiler to the HP turbine, from the HP turbine back through the reheat system, and then from the reheat system in the boiler to the IP or intermediate pressure turbine. From the IP turbine, we take the steam, which has already used up a lot of its energy in the IP turbine. We refer to steam energy as enthalpy, and we take the steam with a lower enthalpy, with a lower energy, and we deliver it then to two low pressure turbines. If I come around here, we can get a better look. We've got the one turbine to the right of the screen where my mouse is, and the other low pressure turbine on the left side of the screen where my mouse is. The final bit of useful working energy from the steam is extracted in our low pressure turbines. But now we've got a bit of a problem. We want to use that water again within our boiler in order that we can turn it to steam and send it back to the high pressure turbine and repeat the entire process again. In order to do that, we need to condense the steam in a condenser, and here we've got two of them. There's one condenser per low pressure steam turbine. And what we're going to do, we're going to cool the exhaust steam from our low pressure steam turbines in order that that steam begins to condense and we get condensate. We cool the steam using our cooling water system, which we can have a look at in the moment, but essentially it just means that we're passing cold water through a heat exchanger, and as the steam comes into contact with our cooled heat exchanger, usually just a series of pipes, similar to a shell and tube type heat exchanger, the steam is going to condense, and then it's going to drip down to the base of our condenser in an area known as the hot well. When this condensate accumulates at the base of our condenser within the hot well, we need to extract it. And we can extract it through these pipes here, and we're going to use a condensate extraction pump, which is this one here, in order to pump the condensate through a series of heaters and then back up to our deaerator. You can see here the condensate's coming from the right side of the screen, passes through the pump. The pump would typically be installed below the condenser, or at least on the same level as it. Here it's in a slightly different place. If we turn around here, you can follow the pipe as it comes out, goes into our low pressure feed water heaters. Here's the first stage, and here is the second stage. And then from our second stage low pressure feed water heater, which is quite a mouthful to say, we send the heated feed water then along this section here, and I won't follow it, but essentially, we can follow it. You can see it coming from the pump along here, into our first stage low pressure feed water heater, into the second stage, and then out through the discharge here, along here, going upwards, and that's going to then go to our deaerator. If you're wondering what heats the feed water heaters, it's actually the exhaust steam from our turbines. The exhaust steam from our high pressure turbine is discharged to our high pressure feed water heaters, and so is the exhaust steam from our intermediate pressure turbine as well. The exhaust steam from the intermediate pressure turbine is used to heat the first stage high pressure feed water heater. The exhaust steam from the high pressure turbine is used to heat the second stage high pressure feed water heater. Likewise, we take some of the exhaust steam from our low pressure turbines and we'll use that to heat our low pressure heaters. You can see the connection coming off here and another one which is coming off here. So that's how we're heating the feed water prior to it going to the boiler. It's simply more efficient than if we allow the feed water to cool down at the various stages and then have to heat it all the way up again. I mentioned that we would talk about the cooling water system, so let's have a look at that. On this side, we've got discharges from our condensers. There's 4 connections, so there's 2 discharges per condenser. They join up into a common pipe, a common manifold, and this pipe then runs towards our cooling tower. You can see here there are 2 pipes connected to the cooling tower. The one where my mouse is now goes to the condenser, so we're delivering cooling water to the condenser. The one here on the left side where my mouse is now is going to the cooling tower. I know this because the water from the condenser, when it's sent back to the cooling tower, is delivered higher up into the cooling tower than when we're drawing it out through the base towards the condenser. The water enters into the cooling tower and is sent into a heat exchanger. You can see it here. And the water is going to drip down through that heat exchanger. Some of it will evaporate, and this will cause the remaining cooling water to be cooled down. That is evaporative cooling. The cooled cooling water is drawn then through this pipe and sent towards the condenser. So we're drawing cooled cooling water out, or cold cooling water, and we're sending back cooling water that has a slightly higher temperature. The reason we're sending it back at a slightly higher temperature is because within our condenser, when we condense the steam, some of the heat energy from the steam is passed to the cooling water temperature increases, the steam temperature decreases, and that's what causes it to change state and become a liquid, which we refer to as condensate. I will say here that condensate is typically from the condenser up until the deaerator. From the deaerator, we then have feed water. After the boiler, we have steam. The only other system that we need to look at now is the electrical system. We've passed steam through our high pressure steam turbine over here. We've then passed it through an intermediate pressure steam turbine. Then we've passed it through 2 low pressure steam turbines. The energy from the steam is transferred to our steam turbine rotors. The steam turbine rotors will then rotate. The steam turbine rotors are connected to a generator rotor. Here is our generator. The generator rotor will rotate as well and will begin to produce electrical power. Important to realise though, we're not actually producing electrical power here, we're just transferring energy from one form to another. We started with coal, which is chemical energy. We released that by burning it. We then transferred the energy to steam as heat, which is a form of kinetic energy. When particles vibrate together, we generate heat. We're then taking the energy from the steam, transferring it to our steam turbine rotors, and will cause the rotors to rotate. At this point we have mechanical energy. We transfer that mechanical energy to our generator rotor, the rotor turns, and at that point we convert the mechanical energy from the generator rotor into electrical energy. And we have electrical power, or what we commonly refer to as electricity. A typical output voltage here would be around 10,500 volts. From our generator, maybe 20,000 volts. It really depends upon the design of the generator. At the end of the generator, we've got a small box. We use this box for excitation, which means we control the magnetic field strength within our generator in order that we can regulate the power output from the generator. So I've now added the connections going from the generator to our electrical transformer. You can see the transformer here. This type of transformer is a liquid insulated conservator type transformer. The transformer components are sitting within a tank, and the tank is full of mineral oil, usually. Sometimes it's full of a different type of oil, such as a natural ester oil, but the mineral oil types are by far the most common. Over 95% of all liquid insulated transformers use mineral oil. We call it a conservator type transformer because we have this conservator tank up here. It's an expansion tank, similar to that which you'd have on a combustion engine if you're looking at the cooling water system, also known as the jacket water system. This power plant must be quite a modern power plant. The reason I say that is because these connections here coming out, they're not the actual connections from the generator. The connections from the generator will just be copper bars, maybe even aluminium, but whatever the material is, it will be a very good electrical conductor. So those bars are going to be sitting within these pipes. These pipes are charged with insulating gas. SF6 is a common insulating gas. So we take the electrical connections, the buzz bars, we take them out from the generator within our insulated piping connections, and we will connect them then via bushings to our electrical transformer. From the transformer, you can see we've also got connections coming from the other transformer, which is connected to our other steam turbine. They connect together here. From our electrical transformer, we're going to feed the electrical connections to an open air switchyard. You can see the switchyard is full of a lot of quite similar looking equipment. You're going to have current transformers here, voltage transformers, surge arresters, electrical disconnectors. The open air switchyard is full of a lot of equipment that's used to protect our generator and transformer from the electrical grid. So we're protecting our equipment from overcurrent, over voltage, over frequency, and things like that. You'll often have SF6 type circuit breakers within an open air switchyard. You'll definitely have disconnectors, these items that we're looking at here, and you'll have surge arresters or lightning arresters also. Once the electrical power has passed through the open air switchyard, it comes to these connections here, and actually feeds upwards, and then it will go to a transmission tower, also known as a power tower, and that represents our national grid. The voltage within this open air switchyard is going to be perhaps 110,000 volts, 220,000 volts, maybe even higher, up to about 380,000 volts. It depends upon the transformer and what voltage we wish to achieve. The transformer's purpose is to increase the voltage from 10,000 or 20,000 volts from the generator up to 110,000 or 220,000 volts, etc. Because we're increasing the voltage, we call this a step-up transformer or a generator step-up transformer, GSU for short. I just want to mention here that this arrangement where a transformer feeds along here and onto the same bus as another transformer is quite unusual. This would not usually occur. The electrical transformers and the generators will usually be fully independent. There's a good reason for this. If a generator should fail or a transformer, then it might mean that our entire steam turbine is out of action and we can't generate power from all of this equipment here within this area. However, we could potentially continue generating power within this area where there's another steam turbine, another electrical transformer, another generator, another boiler, etc. We can't do that if we connect this transformer across here onto the same bus as our other transformer. That's why this arrangement is, in my experience, very unlikely. What's not shown here that you definitely will see within any power station is the electrical switchgear. Typically you'll have switchgear between the generator and the transformer, and then you'll have switchgear between the transformer and the open air switchyard. Switchgear are similar to circuit breakers. When you install switchgear, you're attempting to protect any of the equipment that's installed upstream or downstream of it. For example, if we had a generator fault, then we would want the switchgear that's installed between the transformer and the generator to automatically open and protect our electrical transformer. If the electrical transformer has a fault, then we want our switchgear, which is installed between the transformer and generator, to open and protect our generator. So you will see switchgear installed between all major electrical components because that's the only way you can protect the components from each other should they have an electrical fault. So you should have a good understanding now of just how we take coal and turn it into electrical power. I mentioned at the start of the video that we're going to talk very briefly about biomass power plants and waste to energy power plants. The reason I want to talk about them in this video is because they're quite similar in a way to coal-fired power stations. What we're doing is changing the source of energy. Instead of burning coal, we're going to burn biomass or waste. I want to clarify something here concerning biomass and waste. Waste is often included when people talk about biomass. However, biomass is by definition biological. It consists of biological matter. Waste can consist of many different things. Waste, trash, garbage, municipal solid waste, MSW, whatever you want to call it, essentially it's rubbish. It's all the things that you put in a black bag in your home and then throw in the rubbish bin. So there are two different types of power plant that we're talking about here. The biomass type, which includes bark, wood, paper, husks from cocoa beans, sunflower seeds that have had the oil extracted from them, rape seeds that have had the oil extracted from them, etc. You can also include vegetable oils and animal manure, even sewage, in this category of biomass. Waste is not within this category. Waste is something totally different. It could be plastic, it could be glass, it could be metal, it could be quite literally anything that people throw out of their homes. But like I say, when people talk about biomass, they often just include waste as a part of biomass, which is strictly not true. I've visited a few waste-to-energy plants, and as the trucks arrive, they pass through radiation detectors, which shows you that you don't really know what's being delivered to the plant. In addition to that, there has been cases in the past where people have disposed of explosives, bullets. These have then been burnt on site within the boiler or within an incinerator, and that then has caused damage to the equipment and in some cases loss of life. With a biomass plant, it's quite easy to spot if someone has put explosives, bullets or radioactive material into a truck that's full of tree bark. However, with waste, this is not the case. It's very difficult to separate out the various parts of the fuel. A modern waste-to-energy plant will often recycle some of the material that's delivered to it because this is far more efficient than trying to burn it. For example, if a truck was to arrive with a truck full of waste, we would tip the contents into a large pit. A series of conveyors and grab cranes would be used to feed the material away from the pit, where it can be sorted and then separated out into various different piles. One pile may contain glass, another pile may contain steel, beer bottles, milk bottles, Coca-Cola cans, tomato tins. These are all things that you want to separate out of the fuel system. Once they've been removed, they can be recycled, and the rest of the material can then be fed to the boiler. The reason we're talking about biomass and waste-to-energy plants in this video is because they're quite similar to coal-fired plants. The main difference really relates to the type of fuel used and how that affects the major components of the system. For example, instead of having a coal storage yard, we're going to have a large pit. Trucks are going to arrive, they're going to tip their rubbish, tip their biomass into this pit. If it's a waste-to-energy plant, we may then take this waste and send it for sorting before it's fed to the boiler. A lot of the older plants don't do this, they will just feed it directly to the boiler as it is. And the same occurs with a biomass plant. We're going to burn the biomass or the waste within the boiler, but unlike the coal example we looked at previously, we're going to use a grate for feeding the biomass and the waste into the boiler. What happens next really does depend on what we're burning. With biomass, we can guess the moisture content, the ash content, the sulfur content, and all of these kind of things based on the material that's being delivered. In a waste-to-energy plant, we can't really do this. We don't know what the sulfur content of the waste is, or the ash content, or the moisture content, or even the heat value. Because of this, it's quite tricky to design a boiler that's suitable to burn waste. Generally though, a waste-to-energy boiler will be larger in terms of dimensions than a coal-fired power boiler. Not only that, but the exhaust gas cleaning system will be different compared to a coal-fired power plant. Other than that, the steam systems, the water systems, the electrical systems, they're going to be very similar to what we've seen in a coal-fired power system. Only the type of fuel burnt, the dimensions of the boiler, and maybe the designs of the tubes, and the exhaust gas cleaning systems are going to be different from what we saw with our coal-fired power plant. If you want to use any of the 3D models shown in this video, then head on over to saVRee.com. We've got over 400 engineering 3D models that you can use directly through a web browser in AR or VR. If you want to learn more about engineering, we've got over 45 hours of engineering video tutorials and courses at saVRee.com, and you can learn about valves, pumps, power stations, electrical transformers, and many other common engineering machines and processes. Before you go, don't forget to subscribe to the YouTube channel. Thank you very much for your time.